Just imagine. What if gravity suddenly reversed? Imagine, for just a moment, that you're standing in your living room. Maybe you're holding a cup of coffee. Your feet are planted firmly on the floor. Everything feels normal, safe, predictable. Then, without warning, without even a whisper of forewarning, that cup doesn't just slip from your hand. It rockets upward, smashing into the ceiling with explosive force. But that's not all. Your feet leave the ground. Not gently, not like floating, but violently, as if the earth itself has decided to reject you. Within seconds, you're hurtling upward, accelerating faster and faster, watching your home, your street, your entire world fall away beneath you as you're flung into the sky like a piece of debris from an explosion. This isn't science fiction. This is what would happen if gravity, the invisible force that has held everything together since the beginning of time, suddenly reversed. And what comes next is more terrifying than you could possibly imagine. Before we descend into the chaos of reversed gravity, we need to understand what we're dealing with. Gravity isn't just some abstract concept from a physics textbook. It's the fundamental force that orchestrates everything in your life, every single moment of every single day. It's the reason your blood flows properly through your veins, the reason the atmosphere clings to our planet instead of drifting off into space, the reason the moon orbits Earth and Earth orbits the sun. Sir Isaac Newton first described it in the 1700s, but it was Albert Einstein who truly revealed its nature in his general theory of relativity published in 1915. Einstein showed us that gravity isn't really a force pulling objects together. It's the curvature of space-time itself caused by mass and energy. Imagine space-time as a stretched rubber sheet, and massive objects like Earth create a depression in that sheet. Everything around it naturally rolls toward that depression. Now, what if that depression inverted? What if that gentle curve pulling everything together suddenly became a curve pushing everything apart? Let's paint this picture with absolute clarity. The moment gravity reverses, and physicists call this hypothetical scenario negative gravity, or gravitational repulsion, something unprecedented in the history of our universe occurs. On Earth, gravity pulls everything toward the planet's center at 9.8 meters per second squared. That's the acceleration you feel, though you don't notice it because you've lived with it every moment of your existence. Your body has evolved over millions of years specifically to handle this constant downward pull. Your muscles, your bones, your cardiovascular system, all of it calibrated to function under this exact condition. Now reverse that. Suddenly, everything experiences 9.8 meters per second squared pushing away from Earth's center. Think about what's in your house right now. Every piece of furniture, every drop of water in the pipes, every particle of dust floating in the air. In the first fraction of a second, anything not bolted down becomes a projectile. Books fly off shelves. Tables and chairs launch upward. Windows might hold for a moment, but the pressure differential would soon shatter them. But here's what makes this truly horrifying. You wouldn't float gently upward. You would fall upward with the same violence that you would fall downward from a great height. Within 1 second of gravity reversing, you'd be moving upward at 9.8 meters per second. After 2 seconds, 19.6 meters per second. After 5 seconds, you'd be traveling at 49 meters per second, which is about 110 miles per hour, straight up into the sky. Can you picture yourself in this moment? Take a second and really imagine it. You're in your home, and suddenly the floor isn't there anymore. Or rather, it is there, but it's pushing you away. Your stomach lurches, not from nausea but from genuine acceleration. The ceiling rushes toward you, and you smash into it with bone-breaking force. But you don't stop there. If the ceiling is made of drywall or wood, you might crash right through it. If it's concrete, you might be killed on impact. Those who survive the ceiling impact would burst through their roofs and continue accelerating upward into the open sky. Every human being on Earth, all 8 billion of us, would experience this simultaneously. There would be no warnings, no emergency broadcasts, no time to say goodbye to loved ones. One moment, normal life. The next, complete chaos. Let's track what happens in the first minute, because understanding this timeline is crucial to grasping the full horror of this scenario. At the moment of reversal, designated as 0 seconds, everything begins. By 2 seconds, as we mentioned, you're already moving at about 20 meters per second upward. The air around you is also being repelled from Earth, but here's a critical detail that many people don't consider. Air is fluid, and different parts of it are at different distances from Earth's center. The atmosphere doesn't act as a single unified mass, but as countless individual molecules, each responding to the reversed gravity. This creates turbulence unlike anything Earth has ever experienced. Winds of unimaginable violence would erupt as the atmosphere tears itself apart trying to escape the planet. By 10 seconds after reversal, survivors who made it through their ceilings without fatal injuries are now roughly 500 meters above where they started, traveling at 98 meters per second. That's about 220 miles per hour. At this altitude, if you were above a city, you'd see the most surreal and nightmarish panorama. Millions of people, cars, animals, chunks of buildings, all hurtling upward together in a grotesque reverse rainfall. The roar would be deafening, a combination of wind, screaming, and the sound of civilization tearing itself apart. Streetlights, traffic signals, power lines, all ripped from their moorings, whipping through the air. And remember, it's not just people and objects. Water is also being repelled. Every lake, river, ocean, even the water in the soil, begins to lift. Initially, this might look like every body of water on Earth is simultaneously experiencing a massive wave upward, but within seconds, it becomes clear that this isn't a wave, it's an evacuation. 30 seconds after reversal, you're approximately 4.5 kilometers high, moving at 294 meters per second. The temperature at this altitude is significantly colder than at ground level. The atmosphere typically drops about 6.5 degrees Celsius per kilometer of altitude gained. If you started at a comfortable 20 degrees Celsius at sea level, you're now experiencing temperatures around -10 degrees Celsius, and you're probably not dressed for it. The air is also thinner. At 4.5 kilometers, the atmospheric pressure is about 60% of what it is at sea level. Breathing becomes difficult. Your body, still in shock from the trauma of the initial ascent, now struggles to get enough oxygen. Some people would lose consciousness from the combination of cold, thin air, and sheer terror. 1 minute after gravity reverses, those who began at sea level are now about 29 kilometers high, traveling at 588 meters per second, which is about 1,300 miles per hour. You've now exceeded the speed of sound. You've entered the stratosphere, a region of the atmosphere where commercial jets cruise, though they do so at much slower speeds. The temperature here is brutally cold, around -50 degrees Celsius. The air pressure is less than 1% of what you experienced at sea level. Without supplemental oxygen and protective equipment, you would be unconscious, likely already dead from hypoxia, hypothermia, or the trauma sustained during the initial ascent. But your body would continue upward, accelerating relentlessly. Now, let's address a question you might be asking yourself. Would Earth's reversed gravity affect you uniformly during this ascent, or would it change as you get farther from the planet? This is where Newton's law of universal gravitation becomes important. The force of gravity between two objects depends on their masses and the distance between them. Specifically, gravitational force is inversely proportional to the square of the distance between the object centers. Earth's radius is about 6,300 kilometers. When you're at sea level, you're 6,300 kilometers from Earth's center. When you've ascended 29 kilometers, you're now 6,329 kilometers from the center. The difference is negligible, less than 0.5%. So yes, the reverse gravity pulling you upward would remain essentially constant at 9.8 meters per second squared during this first minute. You would continue to accelerate at this rate until you either hit terminal velocity due to air resistance, or you escape the atmosphere entirely and continue into space. But here's where things get interesting. And by interesting, I mean cosmically terrifying. Terminal velocity is the speed at which the force of air resistance equals the force of gravity, resulting in no net acceleration. For a human body in freefall through Earth's atmosphere falling downward, terminal velocity is about 53 meters per second in a belly-to-earth position, or about 120 miles per hour. But we're not falling downward through increasingly dense air. We're being repelled upward through increasingly thin air. As you rise, air resistance decreases because there are fewer air molecules to push against. This means you never truly reach a terminal velocity. You just keep accelerating, albeit with gradually decreasing air resistance slowing the rate of acceleration. By the time you're in the upper stratosphere and approaching the mesosphere, the air is so thin that it provides virtually no resistance. You're in near vacuum conditions, still accelerating upward at close to 9.8 meters per second squared. Let's pull back for a moment and consider what's happening to the planet itself during these first minutes. Earth isn't just losing its human population. It's losing everything on its surface. Every ecosystem, every species of plant and animal, every microorganism living in the soil or floating in water. The great forests of the Amazon, the Siberian taiga, the African savanna, all of it uprooted and flung skyward. Redwood trees that have stood for thousands of years, torn from the ground, their massive root systems unable to anchor them against a force that affects every atom of their being equally. Animals have no chance. Birds in flight, fish in the sea, insects in the air, all experience the same violent reversal. A bird that was flying, perfectly balanced against normal gravity, suddenly finds itself being flung upward with additional force. It doesn't matter how hard it tries to fly downward toward the Earth. It's fighting against a force that affects every cell in its body. The oceans deserve special attention because their response to reversed gravity would be one of the most visually spectacular and devastating aspects of this scenario. Earth's oceans contain about 1.3 billion cubic kilometers of water. That's an almost incomprehensible amount, roughly 1,300 million trillion kilograms. Under normal gravity, this water is pulled toward Earth's center, pooling in the lowest areas of the planet's surface, creating the ocean basins we know. The pressure at the bottom of the Mariana Trench, the deepest part of the ocean at about 11 kilometers down, is roughly 1,000 times atmospheric pressure. That enormous weight of water is held down by gravity. Now reverse it. The ocean doesn't just lift off like a blanket being pulled from a bed. Water is fluid, and different parts of it are at different distances from Earth's center. The water at the bottom of the Mariana Trench is about 5,500 kilometers from Earth's center, while water at the ocean surface is about 6,400 kilometers from the center. Wait, that doesn't sound right, does it? Let me correct that. Earth's radius is roughly 6,400 kilometers. The ocean bottom at the Mariana Trench is about 6,389 kilometers from Earth's center, while water at sea level is about 6,400 kilometers from the center. The trench bottom is closer to Earth's center, so under reversed gravity, it would experience a slightly stronger repulsive force than the surface water. This would create an inversion. The deepest water would try to rise faster than the shallow water, creating immense turbulence. The ocean would literally turn inside out as it lifted away from the planet. Within the first minute, the shallower parts of the ocean would have risen tens of kilometers, but the bulk of the water, representing such enormous mass, would rise more slowly due to the internal friction and turbulence. Imagine standing on the moon, looking back at Earth during this time. You would see the blue planet that has existed for billions of years beginning to come apart. The oceans would appear to bulge outward, great masses of water reaching into space like tentacles. The clouds, normally held close to the surface, would be racing upward. The atmosphere itself would be visibly streaming away into space, creating a vast halo around the planet. It would be beautiful in the way that destruction on a cosmic scale can be beautiful, terrible, and awe-inspiring. Let's talk about the atmosphere in more detail, because its loss would seal Earth's fate even if gravity somehow returned to normal after a brief reversal. Earth's atmosphere has a total mass of about 5.15 times 10 to the 18th power kilograms, or roughly 5 billion kilograms. It's held to the planet entirely by gravity. The atmosphere is densest at sea level and becomes exponentially thinner with altitude. At sea level, there are about 25 billion molecules in every cubic centimeter of air. At the altitude where the International Space Station orbits, about 400 kilometers up, the atmosphere is so thin that it's essentially a vacuum, though not quite. When gravity reverses, every single molecule of atmospheric gas is suddenly pushed away from Earth. The atmosphere would begin streaming into space like air rushing out of a punctured balloon, except there's no balloon and the air is being actively repelled rather than just escaping due to pressure differential. Nitrogen and oxygen, the primary components of Earth's atmosphere, would be lost within hours to days. Some of the heavier molecules might take longer, but the overall effect would be the same. Earth would become airless. Now, you might wonder, where does the atmosphere go? It doesn't just disappear. Those molecules continue to exist. They're just no longer bound to Earth. Under normal circumstances, gas molecules in the atmosphere move in random directions at high speeds, about 500 meters per second for nitrogen molecules at room temperature. However, most of these molecules don't escape into space because gravity pulls them back down, and they collide with other molecules, creating pressure. With gravity reversed, every molecule is being pushed upward at increasing velocity. Some molecules would eventually reach escape velocity and leave Earth's gravitational influence entirely. Though remember, in this scenario, gravity is reversed, so the concept of escape velocity becomes inverted. The question isn't whether they can escape Earth's gravitational pull, but whether they can overcome the reversed gravity pushing them away. The answer is they wouldn't need to. They would just keep being pushed until they're far enough away that Earth's reversed gravitational influence becomes negligible. Here's a question for you to ponder. If you could somehow survive the initial ascent, maybe you were in a specialized bunker that could withstand the forces, would there be any way to save yourself? What would you need? You would need a structure firmly anchored to bedrock deep underground, with a closed life support system including air, water, food, and temperature control. But here's the problem. Even bedrock would be affected by reversed gravity. The anchor points would need to resist the force of the structure and everything in it being pushed upward at 9.8 meters per second squared. For every kilogram of mass in your bunker, you would need an anchor that could hold it down against that force. A 1,000 kilogram structure would exert a force of 9,800 newtons trying to lift away. That's equivalent to the force required to lift about 1,000 kilograms under normal gravity, which is substantial but manageable with proper engineering. However, we haven't considered the real problem. The Earth itself would be coming apart. Let's examine what happens to the solid Earth when gravity reverses. Earth isn't a uniform sphere. It's a layered structure composed of a crust, mantle, outer core, and inner core, each with different compositions and densities. The crust, where we live, is relatively thin, about 30 to 50 kilometers thick under continents and 5 to 10 kilometers under oceans. It's composed primarily of lighter rocks like granite and basalt. Beneath the crust is the mantle, about 2,900 kilometers thick, composed of denser silicate rocks that, under normal conditions, are under immense pressure and heat. Below that is the outer core, about 2,200 kilometers thick, made of liquid iron and nickel. And at the center is the inner core, about 1,200 kilometers in radius, composed of solid iron and nickel. This layered structure exists because, over billions of years, denser materials sank toward the center while lighter materials rose toward the surface, all orchestrated by gravity. When gravity reverses, this entire arrangement becomes catastrophically unstable. The dense inner core, composed of iron and nickel, is now being pushed outward by reversed gravity. But it's surrounded by the liquid outer core, which is also being pushed outward. And both of these are beneath the mantle and crust. The forces involved are beyond comprehension. The inner core has a mass of about 10 to the 23 power kilograms, that's 100 billion trillion kilograms. all suddenly experiencing a reversed gravitational force. The pressure that normally keeps it solid despite temperatures around 5,500 degrees Celsius would change dramatically. The outer layers of the Earth would be pushed away from the center, but the inner layers would be pushing outward even more forcefully because they're closer to Earth's center and thus experience stronger reversed gravity. Think of it like this. Imagine you have a ball made of concentric layers of different materials, with the densest material at the center. Now imagine that the center is suddenly trying to push itself outward with tremendous force while the outer layers are also being pushed outward, but less forcefully. The result would be catastrophic fragmentation. Earth would literally tear itself apart from the inside out. Cracks would appear in the crust within seconds of reversal. These wouldn't be ordinary cracks. They would be global fault lines, massive rifts splitting continents. Volcanic activity would explode as the mantle material, no longer held down by the weight of the overlying crust, erupted outward. Every volcano on Earth would erupt simultaneously, and entirely new volcanic vents would open as the crust fractured. The time scale for Earth's complete disintegration is difficult to calculate precisely because it depends on the strength of the materials involved and the exact dynamics of the reversed gravitational force. However, geological materials have limited tensile strength. Rock can withstand compression quite well, which is good under normal gravity where everything is pushing together. But rocks are relatively weak under tension, being pulled or pushed apart. Granite, for example, has a tensile strength of about 4 to 25 megapascals, meaning it can withstand 4 to 25 million newtons of force per square meter before fracturing. The forces involved in reversed gravity would exceed this almost immediately on a global scale. Within minutes to hours, Earth's crust would fragment into massive chunks, each being repelled away from the planet's center along with everything else. Imagine witnessing this from space, from a safe vantage point unaffected by Earth's reversed gravity. In the first minutes, you would see the atmospheric halo we discussed, the oceans lifting away, the obvious chaos on the surface. Within the first hour, you would see the continents themselves beginning to break apart. The planet would swell as internal pressure forces the layers apart. Within several hours, Earth would no longer look like a planet. It would look like a cloud of debris expanding into space, a cloud composed of everything that once made up our world. Rock, water, air, the remains of civilization, all of it spreading outward in a growing sphere of destruction. The material closest to the former center would be moving fastest, having experienced the strongest reverse gravity. The material that was on the surface would be moving slower. This would create a density gradient in the expanding debris cloud, with the core material eventually overtaking and passing the crustal material. What would happen to the Moon during all of this? The Moon orbits Earth at an average distance of about 384,000 kilometers. It's held in orbit by Earth's gravity, constantly falling toward Earth but also moving sideways fast enough that it keeps missing. The Moon's orbital velocity is about 1 kilometer per second. When Earth's gravity reverses, the Moon is suddenly being pushed away rather than pulled toward Earth. The Moon's motion, however, is tangential to Earth. It's moving sideways relative to the Earth-Moon line. With reversed gravity, the Moon would follow a spiral path away from Earth, the reverse gravitational force giving it a constant outward push while its tangential velocity carries it sideways. The exact trajectory would be complex, but the end result is clear. The Moon would escape Earth's influence entirely. Over days to weeks, it would drift away, eventually either entering its own independent orbit around the Sun or, if it passes close enough to another massive body, being captured by that body's gravity. Without the Moon, even if Earth somehow survived as a planet, we would lose the tides, and the Earth's axial stability would be compromised over long timescales. But of course, Earth wouldn't survive, so this becomes a moot point. Let's return to the human perspective, because ultimately, this scenario is horrifying not because of the abstract physics but because of what it means for us. Consider the different experiences of people in different situations when gravity reverses. Someone on the ground floor of a building might crash through their ceiling into the upper floor, then through that ceiling, and so on until they exit the roof. Someone already on the top floor of a skyscraper would have a slightly different experience. They would hit their ceiling and then immediately burst through the roof, beginning their ascent from an already elevated position. But here's something particularly nightmarish. People in basements or underground would have multiple ceilings to crash through. The impact trauma would likely be fatal before they ever saw the sky. What about people in vehicles? If you were in a car when gravity reversed, both you and the car would be flung upward. However, you wouldn't stay in the car. The instant gravity reverses, you would be pressed against the car's ceiling, or what was the ceiling and is now effectively the floor, with immense force. If you were wearing a seatbelt, it would cut into you as the car accelerates upward around you, or rather, as you try to accelerate faster than the car. Actually, let me reconsider. Both you and the car experience the same reversed gravitational acceleration, 9.8 meters per second squared away from Earth's center. So initially, you would accelerate together. But cars are made of metal, glass, and plastic. They have different aerodynamic properties than a human body. As you rise and air resistance becomes a factor, the car would experience different drag forces than you. Also, the car's orientation would be unstable. Tumbling through the air at hundreds of miles per hour, it would likely tear itself apart from the aerodynamic forces. You would be separated from the vehicle and continue upward independently. People in aircraft present an interesting case. A commercial airliner cruising at about 10,000 meters altitude is already in the thin atmosphere. The plane is pressurized, and passengers are comfortable. When gravity reverses, the plane and everyone in it is suddenly pushed upward. The plane's engines, which were providing thrust to maintain altitude and forward motion, are now irrelevant. The pilots would have no control. The plane would accelerate upward along with everything else. The passengers, strapped into their seats, would feel the floor drop away. Except it's not the floor dropping, it's them being pushed up into their seatbelts with the force of one gravity. Wait, let me think about this more carefully. If gravity reverses to negative 9.8 meters per second squared, and the plane is also being pushed upward at 9.8 meters per second squared, then relative to the plane, the passengers experience zero net force in the vertical direction initially. But the plane's wings are designed to generate lift in normal gravity. With reversed gravity, those wings would be generating lift in the wrong direction relative to the plane's orientation. The aerodynamics would be all wrong. The plane would become unstable, tumble, and likely break apart from the structural stresses. Once the plane breaks apart, the passengers would be exposed to the elements and continue their ascent individually, facing the same fate as everyone else. Freezing, suffocation, and eventual death in the upper atmosphere or space. Submarines deep underwater face perhaps the strangest fate. The ocean is being pushed upward, and the submarine is a sealed vessel within that ocean. The submarine would rise with the water, but the water itself is experiencing tremendous turbulence as it inverts and lifts away from Earth. The pressure dynamics would be chaotic. Submarines are designed to withstand external pressure pushing inward when deep underwater. With reversed gravity, the internal air pressure would be greater than the external water pressure in some situations, and the structural dynamics would be entirely different from what the vessel was designed for. Most likely, the submarine would be torn apart by the turbulent water and the rapid ascent. Even if it somehow remained intact, it would rise with the ocean water into the upper atmosphere and eventually into space, where it would freeze and lose all its air. Now, let's discuss a disturbing detail that we haven't fully addressed. What do you experience personally, subjectively, as a human being, during the minutes you remain conscious during this ascent? The first sensation is the sudden reversal, a gut-wrenching lurch as your inner ear's vestibular system, which normally tells you which way is down, suddenly screams that down is now up. This would cause immediate, severe vertigo. Nausea would follow within seconds. Then comes the impact with the ceiling, assuming you're indoors. Depending on the height of your ceiling and your position when reversal occurred, you would strike it with significant force. A typical ceiling is about 2.4 to 3 meters high. Under reverse gravity, You would reach the ceiling in about 7/10 of a second, traveling at about 7 meters per second, or roughly 16 miles per hour. That's like jumping off a high platform and hitting the ground, except you're hitting a ceiling. The impact could cause concussions, broken bones, lacerations. If you're lucky, you pass through the ceiling material, drywall, wood, thin concrete, and continue upward. Once you're in open air, rising rapidly, the sensory experience would be surreal. The sound of wind rushing past you, growing louder as your speed increases. The temperature dropping noticeably every few seconds. The view, looking down at the earth falling away beneath you, seeing the curvature of the horizon becoming more pronounced. Other people around you, also rising, some screaming, some unconscious, some already dead. Debris of every kind, cars, trees, pieces of buildings, animals, all rising together in a grotesque swarm. The light would be strange too. As you rise above the thickest part of the atmosphere, the sky would darken. The blue sky we see is caused by Rayleigh scattering of sunlight by atmospheric molecules. Higher up, with less atmosphere above you, the sky becomes darker, transitioning toward the black of space. Your body's physiological response would be rapid and severe. As the air thins, the partial pressure of oxygen decreases. At sea level, oxygen makes up about 21% of the atmosphere, and the partial pressure is about 21 kilopascals. Your lungs and blood are adapted to function at this pressure. At about 5,500 meters altitude, the air pressure is roughly half that of sea level, and the partial pressure of oxygen is correspondingly lower. Your body can adapt to this if given time. People live at these altitudes in the Andes and Himalayas, but they've acclimated over weeks to months. You're experiencing this change in seconds. Your body responds by hyperventilating, trying to get more oxygen. Your heart rate increases dramatically. You feel lightheaded, confused. This is hypoxia, oxygen deprivation. At about 7,000 meters, most people would lose consciousness within minutes without supplemental oxygen. You're passing through 7,000 meters about 24 seconds after gravity reverses. By the time a minute has passed and you're at 29,000 meters, you've been unconscious for at least 30 seconds. But unconsciousness doesn't mean death, not immediately. Your body continues to function for a while. Your heart keeps beating, your lungs keep trying to breathe, even though there's almost no air. The cold is now extreme. At 29,000 meters, we mentioned the temperature is around -50 degrees Celsius. Your body is losing heat rapidly. Hypothermia sets in. Your core body temperature, normally 37 degrees Celsius, begins to drop. At 35 degrees, you experience moderate hypothermia, confusion, fumbling hands, stumbling. But you're already unconscious, so you don't notice these symptoms. At 30 degrees, severe hypothermia, loss of consciousness, which you've already experienced from hypoxia. At 28 degrees, your heart becomes erratic. Below 20 degrees, death is almost certain. How quickly you cool depends on many factors. Your body mass, what you're wearing, whether you're wet. In the extreme cold of the upper atmosphere, with wind from your rapid ascent stripping away heat, you might lose enough body heat to die within several minutes. However, there's another factor we need to consider: the decompression. As you rapidly ascend and the atmospheric pressure drops, gases dissolved in your body fluids come out of solution. This is the same principle behind decompression sickness, or the bends, which scuba divers experience if they ascend too quickly. Nitrogen dissolved in your blood and tissues forms bubbles. These bubbles can block blood vessels, causing pain, paralysis, or death. They can form in your joints, your spinal cord, your brain. In the scenario we're describing, you're ascending much faster than any diver ever has. The decompression is extreme and rapid. Bubble formation would be severe and widespread. This could cause death even before hypoxia or hypothermia. Additionally, At very low pressures, the boiling point of water decreases. At an altitude of about 19 kilometers, at the Armstrong limit, water boils at the normal human body temperature of 37 degrees Celsius. Above this altitude, without a pressurized suit, the fluids in your soft tissues, saliva, tears, the moisture in your lungs, would begin to vaporize. Your body would swell as the water vapor expands. This is called ebullition, and it's rapidly fatal. So, to summarize your personal experience. In the first second, violent acceleration and vertigo. By 10 seconds, severe trauma from impacts, extreme terror, the beginning of hypoxia. By 30 seconds, likely unconscious from oxygen deprivation. By 1 to 2 minutes, death from some combination of hypoxia, hypothermia, decompression sickness, and ebullition. Your body, now a corpse, continues upward, accelerating through the upper atmosphere and eventually into space. In space, the temperature is often described as very cold, but temperature is actually a tricky concept in a vacuum. There's no air to conduct heat away from you, so you lose heat only through radiation, which is a slow process. Your body would eventually freeze solid, but it might take hours. In the meantime, your body would be exposed to solar radiation on one side, which could actually heat that side, while the other side radiates heat into space. The result would be a strange temperature gradient. But all of this is academic because you're already dead. Let's shift perspective and talk about what scientists and researchers have said about gravity, reverse gravity, and related phenomena. First, it's crucial to understand that in conventional physics as we currently understand it, gravity cannot simply reverse. Gravity is always attractive between masses with positive energy density. Einstein's field equations of general relativity describe how mass and energy curve spacetime, and this curvature manifests as the attractive force we call gravity. There's no known mechanism in standard physics that would cause gravity to become repulsive for ordinary matter. However, and this is fascinating, there are theoretical constructs and observed phenomena that involve gravitational repulsion in specific contexts. Dark energy is perhaps the most significant example. In the late 1990s, observations of distant supernovae by two independent research teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, who won the Nobel Prize in Physics in 2011 for this discovery, revealed that the expansion of the universe is accelerating. This was shocking because the gravitational attraction of all the matter in the universe should be slowing the expansion down. The explanation that has gained the most acceptance is that space itself possesses a form of energy, called dark energy, that causes a kind of gravitational repulsion. This repulsion doesn't reverse gravity in the sense we're discussing. It doesn't make objects fall upward, but it does push the fabric of space apart, causing distant galaxies to accelerate away from each other. Dark energy is estimated to make up about 68% of the total energy content of the universe, yet we don't know what it actually is. This is one of the biggest mysteries in modern physics. Another theoretical construct involving gravitational repulsion is negative mass or exotic matter. In some solutions to Einstein's equations, if matter could have negative mass, it would gravitationally repel ordinary positive mass, and ordinary positive mass would attract it, leading to bizarre dynamics. For instance, if you had a ball of negative mass and a ball of positive mass, the positive mass would be attracted to the negative mass and move toward it, while the negative mass would be repelled by the positive mass and move away from it. But because the positive mass attracts the negative mass, they would both accelerate in the same direction, with a negative mass chasing the positive mass in perpetual acceleration. This violates our intuitive understanding of physics and potentially the conservation of energy, which is one reason most physicists believe negative mass doesn't exist. However, it hasn't been completely ruled out, and it appears in some cosmological models and theories about wormholes and warp drives. The Alcubierre drive, a theoretical faster-than-light travel concept proposed by physicist Miguel Alcubierre in 1994, requires negative mass or exotic matter to function. Quantum mechanics introduces its own strangeness related to gravity-like forces. The Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948, is a phenomenon where two uncharged, parallel metal plates placed very close together in a vacuum experience an attractive force due to quantum fluctuations in the electromagnetic field. While this isn't gravity, it demonstrates that vacuum energy and quantum effects can produce forces that act over distances. Some speculative theories suggest that manipulating quantum fields or vacuum energy might, in principle, allow for the creation of repulsive gravitational effects, but we're far from understanding how this could work, let alone implementing it. These are highly speculative ideas, often bordering on science fiction, but they're rooted in real physics and serious theoretical work. Another area worth exploring is gravitational anomalies and anti-gravity research. Throughout the 20th century, there were numerous claims and experiments related to anti-gravity. Most of these were either misinterpretations of data, experimental errors, or outright fraud. However, some legitimate scientists explored whether certain configurations of mass, rotation, or electromagnetic fields could produce gravitational shielding or reduction effects. In the 1990s, Russian scientist Eugene Podkoltnov claimed to have measured a small reduction in weight above a rotating superconducting disk. His results were controversial and have not been reliably replicated, and the scientific consensus is that his effect, if real, is likely not related to gravity. NASA and other organizations have occasionally funded research into breakthrough propulsion concepts, including investigations of whether gravity could be manipulated, but no positive results have emerged. As of now, there's no experimental evidence that gravity can be shielded, reduced, or reversed using any known technology or material. Here's a thought experiment for you. If a civilization far more advanced than ours wanted to reverse gravity, how might they do it? This is purely speculative, but let's explore the idea. They would need to fundamentally alter the structure of space-time around a planet. According to general relativity, mass curves space-time in a way that creates the paths objects follow, which we perceive as gravitational attraction. To reverse this, they would need to create a space-time curvature that pushes objects apart. This might involve surrounding the planet with a shell of exotic matter with negative mass. The negative mass would create a repulsive gravitational field. If you could distribute enough negative mass around Earth in the right configuration, you might be able to create a region where gravity appears reversed. However, the amount of exotic matter required would be astronomical, likely comparable to the mass of the Earth itself. And again, we don't know if exotic matter exists. Moreover, the energy required to assemble such a structure would be beyond anything we can imagine. We're talking about a Kardashev Type 2 civilization at minimum. A civilization that can harness the energy output of an entire star. Alternatively, perhaps there's a way to manipulate the fundamental constants of nature or the properties of spacetime itself. Some theories in quantum gravity suggest that spacetime might not be continuous but made up of discrete units at the Planck scale, which is about 10 to the negative 35 meters. If spacetime has a granular structure, perhaps manipulating this structure could change how gravity behaves. But this is so far beyond our current technology and understanding that it's essentially magic. Arthur C. Clarke famously said, "Any sufficiently advanced technology is indistinguishable from magic." Reversing gravity would fall into this category. So while we can imagine extremely advanced civilizations or future humans with capabilities far beyond ours being able to manipulate gravity in ways we consider impossible, there's no physical basis for it happening spontaneously or naturally. Gravity reversal, as described in our scenario, requires a suspension of the laws of physics as we understand them. Now, let's consider whether there are any natural cosmic phenomena that resemble reverse gravity, even if they're not literally reversing the gravitational force. Supernovae, the explosive deaths of massive stars, involve the outer layers of the star being violently ejected into space. While this isn't gravity reversing, it's an example of matter being expelled outward with tremendous force. The mechanism, however, is not reversed gravity but rather the intense energy released from the collapse of the star's core, which rebounds and blows the outer layers away. The core collapse itself is driven by gravity becoming so strong that it overcomes the nuclear forces holding the star's core together, leading to the formation of a neutron star or black hole. The outward explosion is a consequence of the physics of this collapse, not reversed gravity. Pulsars, which are rapidly rotating neutron stars, emit beams of radiation from their magnetic poles. If you were near a pulsar, you would experience extreme conditions: intense gravitational fields, powerful magnetic fields, and lethal radiation. But gravity would still be attractive, pulling you toward the pulsar. In fact, the gravity at the surface of a neutron star is about 200 billion times stronger than on Earth. If you somehow survived the radiation and tidal forces and stood on a neutron star, you would be crushed instantly. The atoms in your body would be compressed to the point where electrons are forced into protons, forming neutrons. You would become part of the neutron star's crust. Again, not reversed gravity, but certainly extreme gravity. Black holes represent the ultimate extreme of gravity. The gravitational pull near a black hole is so strong that not even light can escape once it crosses the event horizon. Inside the event horizon, space-time is curved so severely that all paths lead toward the singularity at the center. If you fell into a black hole, you would experience spaghettification. The tidal forces would stretch you along the direction of fall and compress you perpendicularly because the gravitational force on your feet would be significantly stronger than on your head, assuming you're falling feet first. This is the opposite of reversed gravity. It's gravity taken to the extreme. However, there are some theoretical aspects of black holes that are intriguing. Hawking radiation, proposed by Stephen Hawking in 1974, suggests that black holes can emit particles due to quantum effects near the event horizon. Over immense timescales, a black hole could theoretically evaporate completely through this radiation. Some interpretations involve particle-antiparticle pairs forming near the event horizon, with one falling in and the other escaping. The escaping particle carries energy away from the black hole. This isn't reverse gravity, but it's an example of quantum mechanics allowing for effects that seem counterintuitive in the context of classical gravity. White holes are theoretical time-reversed versions of black holes. While a black hole's event horizon allows matter and light to enter but not leave, a white hole's event horizon would allow matter and light to leave but not enter. In the equations of general relativity, white holes are valid solutions, but there's no evidence they exist in nature, and they would be highly unstable. If a white hole existed, it would appear to be a source of matter and energy erupting into space, which might superficially resemble the effects of reverse gravity, but again, it's not the same thing. Most physicists consider white holes to be mathematical curiosities rather than real physical objects. What about the Big Bang? In the very early universe, everything was incredibly dense and hot, and the universe was expanding rapidly. This expansion isn't gravity reversing, but rather space itself expanding, carrying matter along with it. In the first fraction of a second after the Big Bang, during a period called cosmic inflation, the universe expanded exponentially, driven by a hypothetical inflaton field. The expansion was so rapid that regions of space moved apart faster than the speed of light. This doesn't violate relativity because it's not matter moving through space faster than light, but rather space itself expanding. This rapid expansion might seem like everything is being pushed apart, similar to reverse gravity, but the underlying mechanism is completely different. It's the dynamics of space-time expansion driven by the energy density of the inflaton field, not a reversal of gravitational attraction. Let's return to Earth and explore what evidence we have about gravity's constancy. Has gravity on Earth always been the same? Measurements and geological evidence suggest that gravity, or more precisely, the gravitational constant, has been stable over billions of years. The gravitational constant, denoted as big G, is approximately 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. This is one of the fundamental constants of nature. Some theories propose that fundamental constants might change over cosmological timescales, but observations of distant quasars, ancient atomic spectra, and other evidence suggest that if the gravitational constant is changed, the change is extremely small, less than 1 part in a trillion per year. For all practical purposes, gravity on Earth has been the same since the planet formed about 4.5 billion years ago. There's no geological or paleontological evidence of gravity ever having been different, let alone reversed. How do we know this? Fossils and ancient rock formations provide clues. The structure of ancient trees, the size and shape of dinosaur bones, the flow patterns of ancient lava, all of these are consistent with gravity being the same as it is today. If gravity had been significantly different, we would see evidence in the geological record. For instance, if gravity had been stronger in the past, trees would need thicker trunks to support their height, and large animals would be more limited in size. If gravity had been weaker, the opposite would be true. The fact that we don't see such variations supports the idea that gravity has been constant. Additionally, the Moon is slowly moving away from Earth at a rate of about 3.8 centimeters per year due to tidal interactions. By studying ancient tidal patterns recorded in sedimentary rocks, geologists have confirmed that this recession has been consistent with our understanding of gravity and orbital mechanics over hundreds of millions of years. Now, let's explore a related question. Could gravity be turned off rather than reversed? What if gravity just stopped? Interestingly, the consequences would be almost as catastrophic, though different in some details. Without gravity, objects wouldn't be repelled from Earth. They would simply continue moving in whatever direction they were already moving due to inertia. Earth rotates, so at the equator, the surface moves at about 465 meters per second. If gravity suddenly ceased, you and everything else would continue moving in a straight line at whatever velocity you had. Since you were on a rotating sphere, your straight-line path would take you tangentially off the Earth's surface and into space. It wouldn't be as violent as reversed gravity, you wouldn't accelerate upward, but the end result would be similar. Everything on Earth's surface would drift away into space. The atmosphere would dissipate, the oceans would float away, and the planet itself would lose its spherical shape because gravity is what compresses Earth into a sphere. The planet would relax, possibly fragmenting into pieces that would drift apart. Actually, the dynamics are more complex. Earth's internal structure is under tremendous pressure due to gravity. The pressure at Earth's core is about 360 gigapascals, which is about 3.5 million times atmospheric pressure. This pressure is entirely due to the weight of the overlying material pressing down. If gravity turned off, this pressure would vanish, but the materials would still have their thermal energy. The core is extremely hot, around 5,000 to 7,000 degrees Celsius. Without gravitational compression, the pressure would drop, but the temperature would remain high initially. The phase of the materials might change. Some of the liquid outer core might vaporize or expand. The entire planet would undergo a complex process of expansion and cooling, likely fragmenting in the process. It's difficult to predict exactly what would happen without detailed simulations, but the key point is that Earth's structure depends critically on gravity. Let me ask you this: if you knew gravity was going to reverse in 24 hours, what would you do? Where could you go? Is there any preparation that could save you? Let's think through this. You can't escape Earth's gravitational influence in 24 hours using current technology. The fastest spacecraft we've built, the Parker Solar Probe, travels at about 190 kilometers per second at its closest approach to the Sun, but it took years to get up to that speed using gravitational assists from Venus. A typical rocket can't achieve anything close to that speed quickly. Even if you boarded a spacecraft immediately, you would still be within Earth's gravitational influence when the reversal occurred, and you would be pushed away along with everything else. Your best bet might be to get as far from Earth as possible so that when the reversal occurs, the force pushing you away is weaker. But in 24 hours, even a fast spacecraft might only make it a few 100,000 kilometers, and Earth's gravitational influence extends much farther than that. The Moon, at 384,000 kilometers, is still very much within Earth's gravitational influence. What if you tried to anchor yourself deep underground? We discussed this earlier. The problem is that the reversed gravity affects the entire planet, including the rock you're trying to anchor to. The bedrock itself would be pushed upward and would fragment. However, here's a thought. What if you positioned yourself at Earth's center? At the very center of Earth, the gravitational force is zero because you have mass pulling you equally in all directions. If gravity reversed, would you experience zero force at the center, or would the dynamics be different? In a perfectly symmetrical, non-rotating sphere, the gravitational force at the center is zero both before and after reversal. However, Earth isn't perfectly symmetrical, and the forces at the center would be complex. Moreover, the center of Earth is a solid iron core at temperatures hotter than the surface of the Sun. You can't physically go there. And even if you could, the planet would be disintegrating around you, so you wouldn't survive long. Perhaps the only scenario in which you could survive is if you were in a self-sufficient spacecraft that was already far from Earth or any other massive body, drifting in interplanetary space. If you were out there when Earth's gravity reversed, you would be unaffected. You would watch from a distance as Earth tore itself apart. You would become a lone survivor, drifting in space, with no home to return to. Depending on your resources, food, water, air, fuel, you might survive for weeks, months, or years. But eventually, your resources would run out. Unless you could reach another habitable planet or a space station with a sustainable life support system, you would die alone in the void. It's a grim scenario, but it underscores the fact that gravity reversal on Earth would be an extinction-level event, not just for humans but for all life on the planet. Speaking of extinction-level events, how does gravity reversal compare to other catastrophic scenarios humanity has considered? Asteroid impacts, supervolcano eruptions, global nuclear war, runaway climate change, a nearby supernova or gamma-ray burst. All of these are existential threats that scientists have studied. An asteroid impact like the one that killed the dinosaurs 66 million years ago released energy equivalent to billions of nuclear bombs. It caused massive fires, a global impact winter, and the extinction of about 75% of species. Yet Earth survived. Life survived. Microorganisms deep in the oceans and underground persisted. Over millions of years, life diversified again. Similarly, supervolcano eruptions, like the Toba eruption 74,000 years ago, caused significant climate disruption and may have reduced the human population to just a few thousand individuals, but humanity survived. Even an all-out nuclear war, while it would be catastrophic and could cause a nuclear winter, likely wouldn't sterilize the planet entirely. Life is resilient. Gravity reversal is different. It doesn't just affect the surface or the atmosphere. It dismantles the planet itself. There's no sheltering from it, no adapting to it. It's absolute destruction. In this sense, it's more akin to the Earth being engulfed by the Sun when it becomes a red giant in about 5 billion years, but even that is a gradual process over millions of years. Gravity reversal, as we've described it, would destroy Earth in hours to days. The only comparable scenario might be if Earth collided with another planet-sized body at high speed, shattering both planets. This actually happened early in Earth's history when a Mars-sized body called Theia collided with the early Earth, creating the Moon. But that was billions of years ago, and the resulting debris eventually coalesced into the Earth-Moon system we have today. A sudden gravity reversal offers no such recovery. The debris would expand into space and never reassemble. Let's explore the existential and philosophical implications. Humanity has always lived with the assumption that certain things are constant. The ground beneath our feet is solid. Gravity pulls things down. The sun rises and sets. These are bedrock assumptions upon which we build our understanding of the world. The idea that gravity could reverse challenges one of the most fundamental of these assumptions. It forces us to confront the fragility of our existence. We think of ourselves as masters of the planet, capable of incredible feats of engineering and technology. We've split the atom, sent probes to the edge of the solar system, decoded the human genome. Yet, we're utterly dependent on the stability of natural forces that are beyond our control. If gravity reversed, all of our achievements would be meaningless. Our cities, our art, our knowledge. All of it would be scattered into space and destroyed. This brings to mind the concept of cosmic insignificance. Earth is a tiny speck in an incomprehensibly vast universe. Our Sun is one of hundreds of billions of stars in the Milky Way galaxy, and the Milky Way is one of hundreds of billions of galaxies in the observable universe. From a cosmic perspective, the destruction of Earth would be utterly insignificant. The universe wouldn't notice. Stars would continue to burn, galaxies would continue to rotate, and the laws of physics would continue to govern the cosmos. This realization can be either terrifying or liberating, depending on your perspective. It's terrifying because it emphasizes how vulnerable and small we are. It's liberating because it suggests that our struggles and conflicts are, in the grand scheme of things, trivial. If Earth were destroyed, the universe would go on, indifferent. Yet, from our perspective, Earth and humanity are everything. This is where we live, where our loved ones are, where all of human history has unfolded. The paintings of the Renaissance, the music of Beethoven, the discoveries of Einstein, the laughter of children playing in parks, all of it exists here. To us, Earth is infinitely precious. The destruction of Earth would be the destruction of everything we know and value. This paradox, that something can be simultaneously insignificant cosmically and infinitely valuable personally, is one of the central tensions of the human condition. Contemplating gravity reversal forces us to grapple with this paradox. It reminds us that we should cherish and protect our world not because it's important to the universe, which is indifferent, but because it's important to us. There's also a meditative quality to imagining our own deaths and the death of our world. Many philosophical and spiritual traditions encourage contemplating mortality as a way to appreciate life more fully. The Stoics of ancient Rome practiced negative visualization, imagining the loss of everything they valued, so that they would appreciate what they had while they had it. Buddhism teaches the impermanence of all things, encouraging acceptance of change and loss. Contemplating gravity reversal is an extreme form of this practice. If you truly imagine the world ending in such a dramatic and absolute way, it might change your perspective on your daily worries. The argument you had with a friend, the stress about work, the anxiety about the future. Do these things matter as much when you consider that everything could end in an instant? Perhaps this thought experiment can help us prioritize what's truly important. Relationships, experiences, kindness, curiosity, the pursuit of understanding. Now, let's consider whether there are any warning signs that could precede a gravity reversal, assuming for a moment that it were possible. If gravity is a manifestation of space-time curvature caused by mass and energy, then a reversal would require a fundamental change in space-time or in the properties of matter. We might expect to see precursor phenomena. Perhaps the gravitational constant would begin to fluctuate. We have incredibly precise measurements of gravity and the gravitational constant using instruments like gravimeters and atomic clocks. If gravity were changing, we would detect it. We might also observe anomalies in the orbits of planets and satellites. The precise positions of planets are monitored constantly, and any deviation from predicted orbits would be noticed immediately. If the Moon started to drift away faster than expected or planets showed unusual orbital changes, it could indicate something wrong with gravity. Additionally, we might see effects in particle physics experiments. Gravity is much weaker than the other fundamental forces, but at very small scales or in high-precision experiments, gravitational effects can be measured. Any change would show up in data. So, if gravity were going to reverse, we would likely have at least some warning from anomalous measurements. Of course, this assumes the reversal is a gradual process rather than an instantaneous switch, which our scenario posits. If there were a warning, how would society react? History shows that humans are not very good at responding to slow-moving threats. Climate change is a prime example. Despite decades of scientific warnings, global action has been slow and insufficient. However, gravity reversal would be different in one crucial way. It would be undeniable and immediate in its consequences. There would be no debate about whether it's real or whether human activity is causing it. It would be a clear, observable phenomenon. If scientists detected that gravity was weakening or showing signs of instability, and if they predicted an imminent reversal, there would likely be panic. Stock markets would crash, governments might declare emergencies, people might riot or flee to perceived safe zones, even though no place is safe from this. Religious interpretations would proliferate. Some would see it as divine judgment, others as a natural cosmic cycle, still others as caused by human hubris or technology. The social fabric would strain and likely break under the pressure of impending doom. Would there be any attempts to stop it or mitigate it? If gravity reversal were caused by some external phenomenon, say, an approaching massive object with unusual properties, or an anomaly in spacetime, scientists and engineers might attempt to devise solutions. But what could we do? Our ability to manipulate gravity is zero. We can't generate gravitational fields, shield against them, or alter them in any way with current or near-future technology. We would be utterly helpless. Perhaps the only thing we could do is preserve some record of humanity's existence in the hope that someone or something might find it in the distant future. A message sent into space, a time capsule placed in a stable orbit around the sun, containing information about who we were, what we achieved, and what we valued. It's a poignant thought, humanity's epitaph drifting through the void, waiting for an audience that may never come. Let's shift to a more speculative angle. Some fringe theories in science fiction have explored the idea of parallel universes or alternate dimensions where physical laws are different. What if there's a universe where gravity is repulsive rather than attractive? What would such a universe look like? In a universe with repulsive gravity, matter would push other matter away. Particles of gas in the early universe wouldn't coalesce into stars and galaxies. Instead, they would spread out, becoming more and more diffuse. Such a universe would be cold, dark, and empty, with no structures forming. Life as we know it couldn't exist because life requires complexity, and complexity requires matter to come together, which requires attractive forces. However, perhaps other forces could play a role. Electromagnetic forces, for instance, can be both attractive and repulsive depending on the charges involved. Maybe in a universe with repulsive gravity, electromagnetic forces or some other force we don't know about could take gravity's place in forming structures. But this is pure speculation, and such a universe would be radically different from ours. Multiverse theories suggest there could be countless universes with different physical constants and laws. If the multiverse is real, there might indeed be universes where gravity works differently. Some theories, like string theory, propose that there are many possible vacuum states, each corresponding to a different universe with different physical laws. Our universe happens to have the laws we observe, but others might have wildly different laws. Anthropic reasoning suggests that we observe the laws we do because only in a universe like ours can observers like us exist. In a universe with repulsive gravity, there would be no one to observe it. It's a strange loop. We can imagine such universes, but they can't produce beings capable of imagining. This connects to the fine-tuning problem in cosmology. Many of the fundamental constants of nature appear to be fine-tuned to allow for the existence of stars, planets, and life. If gravity were slightly stronger or weaker, stars might not form properly, and life might not arise. The fact that we exist suggests either incredible luck, necessity built into the laws of physics, or a vast multiverse where all possibilities are realized and we happen to be in one that permits life.